So we're going to start on our very last topic, which is Markov chains. And as you know, I hope one more homework due on the last day of class, which is next Friday. Almost all the sections are still meeting today and tomorrow because there's really way too much material for one more section. So this week it will focus on law of large numbers, central limit theorem, multivariate normal, which we have been doing. Then the last section next week, then the TFs will do examples of Markov chains, which is our last topic. And okay, so I'll just start from the beginning of Markov chains. There's also a handout that I wrote on Markov chains, which you can read at some point if you haven't seen it already. Just post it under handouts. One other thing, not to scare anyone before Thanksgiving, but the final's on December 15th, so it's not really too soon to start thinking about it. I did post the final review handout, which is 66 pages so there's a lot of stuff you can study. The 66 pages consists of 23 pages of review, and then the rest of it just consists of literally just all the past 110 finals. I've been at Harvard since 2006 and teaching 110 every fall, and I don't really believe in withholding information or some people get access to more exams than others because they have a friend from whatever. This is the entire history of 110 finals. So there are five full-length practice exams, and I think you should be, whenever you can, starting practice. And I posted the solutions to them as well, but you should try your best to resist looking at the solutions, except to check your answer or if you're really, really stuck. So I would highly recommend doing at least 2 or 3 of those exams under as close as you can to exam conditions. That is, your time, time yourself strictly. You have 4 pages of notes, double-sided, that kind of thing. Then after each one, then you can go through it. If you run out of time and you're not done, it's still a good idea to spend some time working on the problem, still without looking at the solutions. And then finally, look at the solutions, study your notes, study everything to see where you can improve. So we've covered everything now except for Markov chains, and so if you're starting on those practice before we've gotten far enough in Markov chains, it's not too much of a problem because in general, the problems are not intended to be in order of the first problem is the first thing we did in the course and so on. It's not really chronological like that. But it has been true every year that I put Markov chains as the last problem and nowhere else. So if you haven't gotten far enough on Markov chains yet, you can just skip the last problem of each year until we get a little further with Markov chains. Everything else we've covered the material, so the sooner you start practicing, the better. Okay, so you can assume that the style would be similar to those past exams, and that will give you a good sense of everything. And okay, so Markov chains. What is it? Well, they were invented or discovered, depending on your philosophical point of view. They were invented or discovered by Markov, who we've already heard of through Markov's inequality. He introduced them just over 100 years ago. I think it was 1906. And I'll tell you a little bit about Markov's original reason for studying Markov chains. But that the number of applications they found since then has just been unbelievable, and a lot of directions it's gone in that Markov would not have anticipated. So Markov chains, it's an example of a stochastic process. So I'll tell you just very briefly what a stochastic process is. It's one of the most important examples of stochastic processes. A stochastic process, we've been dealing with, originally we were dealing with one random variable at a time, and then we were sometimes doing 2, and with the central limit theorem and law of large numbers, we were looking at sequences of random variables, right? So sometimes we have sequences of random variables, and we're studying the sample mean and let n go to infinity, stuff like that. But when we were considering these sequence of random variables, mostly we've been assuming that they're IID, right? The central limit theorem and law of large numbers. There are more general versions of those theorems, but we've been assuming IID, which is a very strong assumption, right? Independent, identically distributed. So a Markov chain is an example of a stochastic process, which basically just means random variables evolving over time. Okay, so I'll just say examples of stochastic processes. So what does that mean? I mean, it doesn't literally have to be time, but that's the most common interpretation. So we have this sequence of random variables, x0, x1, x2, blah, 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 blah. We've been looking mostly at the case where these are IID. So we can think of the subscript as time, but if they're IID, then it's just like saying it's resetting every time to a fresh independent random variable. So from a stochastic process point of view, more interesting is when these kind of evolve in some way where there's some kind of dependence, right? But if we allow these to be completely dependent in some arbitrarily complicated way, that can be extremely complicated, right? You have this infinite sequence and they could all relate to each other in some very complicated way. So Markov chains are kind of a compromise. It's basically going one step beyond IID, right? So that they're going to become dependent, but it's in a very special way that I'm going to tell you about that has very, very nice properties. Okay, so we're going to think of the of xn as the state of a system. So it can be interpreted very, very generally. You have just any kind of system. We'll see examples. That you're imagining some kind of like particle or whatever that's wandering around randomly from state to state. It's jumping from state to state, and that's at time n, which we're assuming is discrete right now. That is n is a non-negative integer. So we can consider stochastic processes in continuous time or continuous space, continuous time or discrete time, continuous space or discrete space. So there's basically four possibilities. That is this index, here we just did x0, x1, x2. If we want a continuous time, we could just look at xt, where t is time, which could be continuous. Okay, then we'd have a collection indexed by a continuous variable. Here we're just indexing it discretely. Okay, so this is discrete time. So in Stat 110, we're only going to look at discrete time processes. If you want to go further into stochastic processes, I highly recommend Stat 171, which is an entire course on stochastic processes. We're going to do Markov chains in discrete time. So this is discrete time. And we're assuming discrete space. Continuous space would mean that each of these x's is allowed to take values like let's say any real number or values in some continuous space. But for our purposes, we're going to assume that each xj takes values in some discrete space, and actually we're going to assume it's a finite space to make things easier. So we're going to be looking at Markov chains where we have finitely many states, and each of these x's is one of those states, and we just have this process that's bouncing around randomly from state to state, and then we want to describe what's the Markov property. Okay, so here's the Markov property. That is what does Markovian mean, and then I'll tell you a little bit about why did Markov introduce this and what are some examples. The Markov property is a certain conditional probability statement. It says, if we look at the next, our interpretation is think of xn as the current state. I mean, I don't know how to define the word now, right? But we have some intuitive conception of now, right? Now is now, that's the present, and then after now is the future, and before now is the past, right? So a lot of Markov chain stuff you can understand intuitively if you think about past, present, and future. Okay, so let's think xn is right now, and we want to predict the future. We want to know what's going to happen at time n plus 1, because we're letting time be discrete. So one step in the future. You can think of xn as today, xn plus 1 is tomorrow. Okay, we want to know what's the probability that xn plus 1 equals j, where j is just some state. And we're usually going to assume that the states are numbered from 1 to capital M, just as a convention. But there's no rule that says you have to do that. We're assuming there's finitely many states. So we're saying, what's the probability that the state of the system tomorrow is state j, given the entire past history of everything? So we're given, well, what's the state today? Xn equals I. And what was the state yesterday? Yesterday was xn minus 1. It was at xn minus 1, and maybe that's in minus 1. And xn minus 2 is in minus 2, all the way back to the very beginning. And x0, let's say it's I0. Okay, so this is saying what's the probability of a certain state tomorrow given the entire past history of the system, right? That looks very complicated, right? It took a lot of time even just to write all these things and all these dots, and this is a big, complicated thing. In a general stochastic process, maybe you can't simplify this very much, okay? But this is too complicated. The Markov structure means that only the most recent information matters. We can get rid of everything else. So this just becomes xn plus 1 equals j, given xn equals I. You can get rid of all the rest. So all these concepts that we've been doing the entire semester are come back here, right? The difference between independence and conditional independence. We're not saying that the past is independent of the future, but we are saying if this property holds, in words, this says that the past and future are conditionally independent given the present. So that's kind of a handy, intuitive way to remember it. So past and future are conditionally independent given the present. Okay, that's exactly what this statement says, given the present. That is, if we know the current value, xn, if we know that, then anything that's further back is just obsolete, outdated information which we can just get rid of. So I just crossed out everything further back in time, right? Only the most recent one matters, conditionally. If we didn't get, that doesn't mean though that if we had xn plus 1 given xn minus 1 and we were not given xn, it doesn't mean we can get rid of the xn minus 1, right? It's conditional independence. So that's the Markov assumption. Whether that assumption is good or not for a real example completely depends on the problem, okay? But that's the Markov property. And in particular, for our purposes, let's actually assume that this doesn't depend on n. So we'll usually call this thing Qij, or call it whatever you want. That's called a transition probability. So sometimes this is called a homogeneous Markov chain. And but a lot of times people will not bother to say the word homogeneous, so you have to be a little careful from the context. Is it assumed to be homogeneous or not? Homogeneous means that this doesn't depend on time, right? So this is saying we're looking at the case where the probability, if the system is at state I, and then we want to know what's the probability that at the next time point it's at state j, if that's always Qij, if it doesn't change with time, then we would say that that's homogeneous or time homogeneous. And the most, for our purposes, we're just going to be studying homogeneous Markov chains. So these Qijs don't depend on n, because that's a nicer case to look at. Okay. So just to have a mental picture in mind, I just made up a simple little example. It really helps to have pictures in mind. So here's one Markov chain. You can make up your own, but here's one I just made up. So there are 4 states we can represent as ovals. Let's number the states 1 through 4. Okay, and then to specify the Markov chain, we just need to specify transition probabilities. That is, what's the probability of going from state 1 to state 2, all different states. So it may not be possible to go from any state to any state in one step. In fact, usually it's not possible. So for example, there's just an example I made up. let's say the system is at state 1, it has probability 1/3 of staying there, and it has probability 2/3 of going to state 2. I'm just drawing arrows, and I'm putting probabilities on the arrows that reflect the probabilities of those different transitions. From state 2, it's equally likely to go back to state 1 or to go to state 2. I guess I'm putting the probabilities above the arrow. So from state 2, it either goes here or here, equally likely. From state 3, it either goes back to state 4 with probability 1/4, or it goes to back to state 1 with probability 1/2, or it stays there with probability 1/4. And then let's say from state 3, just to make life a little bit easier, from state 3 it always goes to state 4. So I'll just put a 1 there. You can make up your own example. Anyway, it just helps to have a picture like this in mind. And for, you can have a Markov chain that has infinitely many states, and then you can't actually draw infinitely many states. But we're only going to be looking at the case where there are finitely many states. So you can always, for our purposes, you can always imagine a picture like this. We have some number of states, and then you have like a particle randomly bouncing around between states, following the arrows, and the arrows may have different probabilities. Okay, that's the mental picture. And then to explain in that picture, what does this property say? It says that you're wandering around from state to state like that, and then what this says is, if I want to know the future or predict the future, all I care about is the current state. I don't care about the whole history of all the long wanderings throughout time to get there. It doesn't matter how you got there, it only matters where you are, right? That's what the Markov property says, intuitively. Okay? So we have these transition probabilities Qij, and we can write that as a matrix. That's called the transition matrix. So we can always just draw a picture like this, but sometimes it's easier to work with a matrix rather than having to draw a picture every time. So we can encode the same information as this picture, just written in matrix form. So the transition matrix, usually we call Q in this course, but you don't have to call it that. That's just the matrix of all the Qij's, all the transition probabilities. So for this example, it's going to be a 4x4 matrix. And then I'm just going to write, what's the probability of going from 1 to 1? That's 1/3. Because there's this loop there, that's probably 1/3. Probability of going from 1 to 2 is 2/3. From 1 to 3 or 1 to 4 is 0. It can't go there in one step. It can go there in more than one step. Okay, then from state 2, it either goes back to state 1 or it goes to state 3. With equal probabilities. So this will be 1/2, 0, 1/2, 0. Okay. From state 3, it always goes to state 4. So it's just going to be 0, 0, 0, 1. Right? I'm just writing down these Qij's as a matrix. And then from state 4, it either goes back to state 1, that had probably 1/2, or it goes to state 3, that's 1/4, or it stays at state 4, that's 1/4. So that would be the transition matrix. Notice that every row sums to 1. And again, it's just a convention. Some people would use the transpose of this matrix instead, and then the columns sum to 1. It's just a convention. We're going to take the convention that we write it this way, that the ij entry is the probability of jumping from I to j in one step. So therefore, all the rows, each row sums to 1. Right? Okay, columns may or may not sum to 1, but the rows sum to 1. So we want to go the other way around and say, what's a valid Markov chain transition matrix? Well, we could just write down a blank square matrix, fill in any numbers you want, as long as they're non-negative, and each row sums up to 1. And then you can easily see how you would then convert that to a picture like this, right? Just drawing arrows with probabilities, okay? So that's what a transition matrix is. By the way, the two most important concepts, just other than the basic, definition of, Markov property, two most important concepts we're going to need. One is transition matrix. Now you know what a transition matrix is. The other one's stationary distribution, which we'll talk about later. Okay, so that's the Markov property. So to tell you a little bit about the history. Well, okay, so how it's used now, it's being used now in two sort of different ways. One is as a model that's might be used in various problems in social sciences, physical sciences, and biology, where you actually literally believe that you have a Markov chain, okay? Or you're using it as an approximation for some system evolving over time. That's very, very useful. But that's sort of limited in the sense that this seems like a pretty strong conditional independence assumption. Like you can forget the entire past as long as you have the present. Well, so there have been thousands of pages of debates about whether if you take the stock price over time, is that Markovian or not? Or is the weather Markov? Things like that. So those become empirical questions which you can study. But one thing to point out though is it's not as limiting as it looks in the sense of that this is sometimes called a first order Markov chain where you're only going one step back. You can generalize this easily to the case where the conditional independence is that it depends on xn and xn minus 1. And it turns out that to understand how that kind of thing works, the right starting point is to be looking at this anyway. So you can extend this and consider Markov chains where it goes 10 steps back or things like that. But anyway, that's still kind of an empirical question. Is that useful for a real system or not, or is that too strong of an assumption about this conditional independence? But another way that this is used though is for Markov chain Monte Carlo, which essentially created a revolution in scientific computing, and it's being used everywhere. And I like to challenge people, find an example of some major field of study where Markov chain Monte Carlo has never been applied. And no one has successfully met that challenge yet. Let's say you're interested in French poetry. You can find Markov chains being applied to French poetry. So why is that? Do you really want to think of French poetry as actually following this model? No, but that's the idea of Markov chain Monte Carlo is that you don't have to worry about whether the actual process you're observing follows a Markov chain. Markov chain Monte Carlo means that you synthetically construct your own Markov chain. So you then can't argue is it Markov or not because you built your own chain, right? Why would you want to build your own chain? Well, the idea, which is a very beautiful, one of the most useful and beautiful ideas of the 20th century, in my opinion, is that you can construct your own Markov chain that will converge to a distribution that you're interested in. So suppose you're trying to simulate some complicated system, and the computations are too hard to do everything analytically and explicitly. There's some extremely clever ways to construct a Markov chain synthetically that will converge to the thing you're interested in. And so then you just program your Markov chain on the computer. So this is a very recent thing, because we need to have fast computers in order for this to be useful. It's a recent idea. You program your Markov chain on the computer, run the chain for a long time, and then you use those results to study the distribution that you're interested in. So that's the idea. I'm just going to write the acronym MCMC. We don't really have time to talk more about MCMC than that, but Markov chain Monte Carlo is just getting more and more popular, widely used every year as a way of doing extremely complicated simulations and computations that would have been completely impossible like 50 years ago, or even 30 years ago. Okay. That's Markov chain Monte Carlo. So Markov chain Monte Carlo is when you build your own Markov chain, right? And then the other application is just that you have this natural system that you choose to model it using a Markov chain. So those are two important but different uses of Markov chains. Okay, so both of those ideas are very, very different from what Markov himself originally had in mind. When he introduced Markov chains, it was actually to help settle a religious debate over the existence of free will, kind of a religious philosophical thing. So at the time, you know, this was early 1900s, the law of large numbers had recently been proven, like here, we recently proved the law of large numbers, okay? And I told you the story of the athlete who was very upset about the law of large numbers because it said that in the long run he'd always be average, and so he couldn't improve, and so he hated statistics, which is kind of like ridiculous, but that was actually very similar kind of concern that people had when the law of large numbers was first proven, which was that you know, some of the philosophers were upset that the law of large numbers might prevent us from having free will, because it says, you know, in the long run, you know, converge to the mean. Where's the scope for having free will then, right? It's saying it will converge to this, right? Where's free will? Okay, so one of Markov's rivals tried to rescue free will by saying, well, the law of large numbers assumes IID, and human behavior is not IID, therefore we're okay, right? Okay, but that, you can see that's not a very convincing argument, because we proved that if the random variables are IID, then the law of large numbers holds, but we didn't show that if it's not IID, then the law of large numbers doesn't hold, and there are more general versions. So what Markov wanted to do was to find a process that's one step in complexity beyond IID, right? That's what this is, right? The IID case would say you can just completely forget everything you're conditioning on, and he wanted to go one step in complexity beyond IID, where you go one step backward, right? So go one step forward in thinking by going one step backward in conditioning. You're going one step beyond IID, and then he proved a version of the law of large numbers that applies to Markov chains, and then they said, well, look, you don't actually need IID in order, you know, for the law of large numbers to hold. Okay, and the chain that he originally looked at, which might be the first Markov chain, was he took a Russian novel and he kind of just empirically was looking at consonants and vowels, and he said, okay, there are two states, vowel and consonant, and you know, a vowel is either followed by a vowel or a consonant is either followed by a vowel or a consonant, and then he kind of empirically computed the probability that, you know, vowel is followed by vowel, vowel is followed by consonant, and so on. And he was just studying that simple chain. So just like this picture, except even simpler, only two states. And I drew one with four states, but you know, conceptually it's the same thing. You're just bouncing around between states. Okay? So that's the whole idea of a Markov chain. And you know, if you keep these simple pictures in mind, it will make things much easier, even for more. You know, we could have a Markov chain that has 10 to the 100th states, but you can still keep pictures like this in mind. Okay? So we've defined the transition matrix. It's just this matrix of transition probabilities. But I want to show you how do we actually use the transition matrix to get, you know, higher order things like what's the probability. For example, we want to answer the question, this is the probability of going, you know, from I to j in one step. What's the probability of going from I to j in 2 steps or 10 steps? Things like that. So those questions can be answered in terms of the transition matrix. Okay, so let's do that now. So suppose that we start the chain. So suppose let's say that at time n, which we're considering as the present, xn, the chain, which is xn at time n, has distribution which I'm thinking of as S, which is a row vector, which we're going to think of as, in other words, we can think of it as a 1 by M matrix. And all I mean by this is we're taking the PMF, but since we're assuming, I'm assuming that there are M states, so here M equals 4 in this example. M is the number of ovals in this picture. So we're assuming M states, and we're saying, okay, the distribution, I just mean the PMF because it's discrete, but since there are only these finitely many values, we may as well just list them all out, right? So this is you know, this thing is the PMF kind of just listed as a vector, listed out, right? So it's the probability, you know, of being in state 1, probability of being in state 2, and so on. Just list out the probabilities. Okay, so in particular, we know that S is a vector, and we're writing it as a row, and the entries are non-negative and add up to 1. Okay, so let's assume that's how things stand at time n, and then we want to know what happens at time n plus 1. So we want to know, you know, what's the probability that xn plus 1 is some state j. So we want to know the PMF. This is the PMF at time n. It's just we're writing it as a vector because that's convenient. That's the PMF at time n. Now we want the PMF at time n plus 1, one step in the future. Okay, well, to do that, it's not hard to guess that what we should do is condition on the value now, right? Condition on what we wish that we knew. It would be convenient if we knew where the thing is now. That would be very useful, right? So we're just going to condition. So we're going to sum over all states I of the probability that xn plus 1 equals j given xn equals I times the probability that xn equals I. Right? Just the law of total probability. But these are things we know. Just by definition, this is qij. That is the probability of going from I to j. By definition, that's qij. And this thing here is just si, right? Because that's just the probability of being at I, and that's just the ith value in this vector. That's just si. I'm going to write it on the left because it looks a little bit nicer to me. So that's the answer as a sum, but it's easier to think of this in terms of a matrix. This is, in fact, the jth entry of S times Q. Where remember, Q is an m by m matrix, and S is a 1 by m matrix, so it's valid to multiply these. The inner numbers match up, and then the dimensions of this are the outer numbers, 1 by m. So S times Q is a 1 by m matrix. And if you just, you know, you don't need a lot of matrix stuff in this class, but I'm assuming you can at least multiply matrices. How do you multiply matrices? Well, you take a row of this and do a dot product with a column of this. And what you do, when you do that, it's exactly this sum, right? You're just going like row times row dot column, and you're adding this up. Okay, so the interpretation of this sum is that it's just the entry of this vector times this matrix. Therefore, S times Q is the distribution, or, you know, PMF written as a vector at time n plus 1. Okay? So that's now playing the role of S. So by the same argument, if we do SQ squared, that's the distribution at time n plus 1. N plus 2, sorry. Two steps into the future. And SQ3, SQ cubed, is distribution at time n plus 3, and so on, because it's just the same thing again, right? Because now S times Q is now playing the role of S, right? And it says, so what this calculation says is to go one step one step to the future, multiply on the right by q. So we multiply sq by q, we get sq squared. Multiply this by q, we get sq cubed. And so on, okay? So what that says is that powers, if we multiply the initial vector of probabilities by q to a power, then that gives us the distribution, that number of steps in the future. So this is saying that I mean, of course, this is going to be pretty tedious to do by hand for most problems, but you know, using a calculator or computer that can multiply matrices, then it just says take powers of q. You don't need to like think that hard each time. It's just use powers of q, and you know how this is going to evolve. Okay, so similarly, by definition, q gives the one-step probabilities. So the probability that xn plus 1 equals j given xn equals I, by definition, that's just qij. Okay, but suppose we wanted the two-step thing, xn plus 2 equals j given xn equals I. Okay, this is a similar calculation to what we just did. So this is the transition probabilities. This is saying go one step ahead in time. And now this says, what happens if we only know xn, but we want to predict 2 steps ahead? Well, it's not hard to figure out what to condition on, right? The missing link here is xn plus 1. That's what's missing. So clearly we should condition on xn plus 1. So let's say we condition on xn plus 1. So this is probably xn plus 2 equals j given xn plus 1 equals, let's say, k, xn equals I. I'm just conditioning on xn plus 1, right? Because that's the missing intermediary that we want. X times the probability xn plus 1 equals k given xn equals I. That's just the law of total probability, the conditional version. Everything is given xn equals I. Let's simplify that into something that's more interpretable. First of all, the Markov property says that if we know the value at time n plus 1 and the value at time n, this is obsolete. That's irrelevant now. So because of this conditional independence, we only want the most recent value, right? So we can get rid of that. So by definition, now we're just saying we're going in one step from k to j. By definition, that's just the transition probability qkj. And then this one is also one step, right? This is saying go from I to k in one step. And again, I'm going to write this on the other side just because it looks nicer. qik, qkj. I just swapped the order of the two terms to make it look nicer. We've expressed it in terms of two one-step things, okay? And now a sum that looks like this, that's of this form, it has a nice interpretation in terms of matrix multiplication again. This is just the ij entry, row I, column j, of q squared. Because, well, why is that true? Well, just think of how do you do q squared? You do q times q. So you take a row of q and dot product with a column of q, and you'll get this. Okay? So similarly, same idea. If we want to know what's the probability, just repeating the same argument, we want to know, like, what's the probability that x, let's say, I don't know, m steps in the future, xn plus m equals j given xn equals I. So this is saying it's at I now. What's the probability that it will be at j m steps in the future? That's just going to be the ij entry of q to the m. So works out pretty nicely. powers of the transition matrix actually give us a lot of information. We don't need like a separate, study of every different, transition and different number of steps. Just work with powers of the transition matrix. Very, very nice. Okay, so just a couple more quick concepts. Well, one that's not so quick is the notion of a stationary distribution. And I'm going to define it now, but we'll talk about it in detail next time. But I just want to mention it now just because it's one of the most important ideas. Transition matrix and stationary distribution are the two most important ideas other than the basic definition. So what's a stationary distribution of a chain? This is also called a steady state or long run or equilibrium, that kind of thing. It's supposed to capture the idea of, so the reason it's important, one reason it's important is if we run the chain for a long time, we want to know, does it converge to some limiting distribution? Okay, and under some very mild conditions, the answer is yes, it will converge to something that we call a stationary distribution. Okay, so that's going to be very important for describing how the chain behaves, especially in the long run, but it's also just useful for other things too. So we say that S, which is a probability vector, 1 by m again. So again, we're just thinking of that as like a PMF written as a row. And the definition is that this is stationary for the chain, for the Markov chain that we're considering, if S times Q, which is one, just to make sure this makes sense again, this is a 1 by m times m by m, so this is going to be a 1 by m matrix, if S times Q equals S. Okay? So I'll tell you the intuition for this definition, but first of all, for those of you who've seen eigenvalues and eigenvectors before, this is pretty reminiscent of an eigenvalue-eigenvector equation. Usually you see eigenvalues and eigenvectors written the other way, like a matrix times a vector, but if you want to write it that way, just take the transpose of both sides. So it's exactly an eigenvalue-eigenvector equation, for those of you who know what that is. If you don't know what an eigenvalue is, well, you should learn, but you don't need to know it for this class. Okay? Now, for the intuition, we just showed, a few minutes ago, we just showed that if the chain at time n follows the distribution S, then this is the distribution one step later in time, right? So if SQ equals S, it says if it starts out according to S, one step forward in time is still following S. That's why it's called stationary, right? Because it didn't change. And if we go another step forward in time, the distribution is still S. And we go one more step, it's still S, right? So if the chain starts out of the stationary distribution, it's going to have the stationary distribution forever. It doesn't change. That's why it's called stationary. Okay? Well, there are a lot of questions we can ask, though. I won't quite call this a cliffhanger, but there are some important questions we can ask, right? One is, does a stationary distribution exist? That is, can we solve this equation? Now, even if we solve this equation, if we got an answer that had like some negative numbers and some positive numbers, that's not going to be useful, right? So we need to solve this for S that is non-negative and adds up to 1. So does such a solution exist to this equation? Does it exist? Secondly, is it unique? Thirdly, I just kind of said, just now, I just kind of said intuitively that this has something to do with the long run behavior of the chain, right? But this definition doesn't seem like it has anything to do with any long run or limits, right? This is just S times Q equals S. So does the chain converge to S in some sense? And we'll have to talk more about what that means and whether it's true. Okay, and then there's a more practical question. Assuming that it exists and and it's this beautiful thing that tells us the long run behavior, there's still a question of how can we compute it, right? So How can we compute it? So those are basic questions about stationary distributions. Okay, and so under some very mild conditions, the answer will be yes to all three of these first three questions. There are a few technical conditions that we'll get into, but under some mild technical conditions, it will exist, it will be unique, the chain will converge to the stationary distribution, so it does capture the long-run behavior. As for this last question, though, how to compute it, I mean, in principle, if you had enough time, you can just, use a computer, or, well, if you had enough time, you can do it by hand, in principle, solve this equation, right? This is just even if you haven't done matrices before, you could write this out as some, enormous linear system of equations, and if the solution exists, in principle, you could find it. You eliminate variables one by one, okay? But that, might take hundreds of years, right? So can we compute it efficiently without spending years doing tedious calculations, or even with a computer, it may get, too nasty of a calculation. Okay, and so the answer to that, in general, in the very general case, is that it may be an extremely difficult computational problem. But we're going to study certain examples of Markov chains where we can not only compute it, we can compute it very quickly and easily without actually having to even use matrices at all. So there's one really nice case that we're going to look at. Not today, though. So, okay, so that's all for today. Happy Thanksgiving, everyone.